We have seen Ford-Fulkerson based algorithms for finding the maximum flow in a flow network. Today we are going to see another approach for solving the max flow problem, which is based on push and relabel operations in a flow network, and that is what we are going to discuss today. Push relabel algorithms for max flow. What push relabel algorithms do? We can try to understand what basically they are doing. Consider a flow network. So given a flow network like this, there is no flow, so you can say that all the flows are zeros. Not that all these labels represent capacities of conduits. So considering flow value across every conduit as 0, you know that the residual network induced by that flow, where f is 0 for all the conduits, the residual network is the same, which we have already seen. And what a Ford-Fulkerson based algorithm do is, it finds an augmenting path and then it sends a flow through that augmenting path. The capacity here is 12, and that 12 unit of materials can travel to the sink from the source along that augmenting path. So this is what a Ford-Fulkerson based algorithm do. So basically, such an algorithm needs to find an augmenting path, which is a source to sink path in the residual network, and send a flow along that path with value same as the capacity of that path, in this case 12. We have seen two such algorithms. One is finding an arbitrary path and the other one is finding the shortest path, one of the shortest path. Now we can see what a push relabel algorithm will do. Push relabel algorithms works in a more localized manner, looking at one vertex at a time and pushing flows to the neighbor vertices only. So if you look at this vertex, it's not going to find a path to the sink. Rather, it looks at only the neighboring vertices and it see how that particular vertex can send flow to the neighboring vertices. And to enable this, these algorithms relax the flow conservation property. Recall that for any flow, the flow conservation property says that if you look at an intermediate vertex, the total flow reaching that vertex must be same as the total flow leaving that vertex. That is an essential property of a flow, and push relabel algorithms relax it as follows. It says that the total flow coming to that, going out of that vertex, minus the total flow coming to that vertex must be greater than or equal to 0. Sorry, the total flow going out of that vertex minus the total flow coming to that vertex must be greater than or equal to 0. Or in other words, if you look at any intermediate vertex, the total incoming flow is greater than or equal to the total outgoing flow. That is the relaxed flow property, and this must be true for all vertices other than the source and the sink. And now this enables you to send a flow of value 16 to V1 and 13 to V2 from S, and not that now the total incoming flow here is 16 and here it is 13, and which is not forwarded to any other vertices, and which is allowed by this relaxed conservation property. I think now you are getting why such a relaxation is required. To work locally, that is required. Otherwise, whatever amount leaves the source must reach the sink, and any flow must satisfy this, and therefore the new relaxed condition defines a special kind of flow which is known as the pre-flow. Not that now V1 and V2 are not satisfying the original flow conservation property, that whatever quantity reaches here, say 13, must leave it. That is relaxed, and the new flow is what is called a pre-flow, because any flow must satisfy the flow conservation property which is relaxed, and the relaxed flow is what is called pre-flow. Now you know that at every vertex there can be some excess flow, that is the total flow reaching there minus the total flow leaving that vertex, which is what is called the excess flow at a vertex. For example, here the excess flow, the E value of V2 is 13 and the E value of V1 is 16, and during the processing intermediate vertices are assumed to have arbitrary capacity to store excess flow. So here there is a value of 13 and here it is 16, and all these intermediate vertices are assumed to have infinite capacity or enough capacity to halt the excess flow whatever it is. This is an assumed property, and when the method finds a max flow, at that time all the excess flow at vertices, at intermediate vertices, will be sent back to the source vertex, so that the excess flow will become 0 at all the intermediate vertices, and at that time you will get a flow, because it is going to satisfy the flow conservation property. An example illustrating the process will make all these things clear. So let us proceed. Now suppose you are given with a flow network, and now all the flow values are 0. So you look at the corresponding residual network. Note that here F is having 0 values on all the contours. So naturally this is the residual network. So what you can do, you start with the source, and you found that you are only looking locally. You found that there are 2 neighboring vertices, and what the source will do is it will send maximum flow along the outgoing contours or edges to the neighboring vertices. So you can see that now here a total of 29 unit of materials is flowing out, and that is why the excess flow, if you just apply the formula, the excess flow will become minus 29, and here the excess flows are 16 and 13 respectively. And the operation which sends flows to the neighboring vertices is what is called a push operation, and that is how the name of that algorithm is getting the push in its name. The operation which sends flows to the neighboring vertices is what is called a push operation. Now you have a flow, pre-flow. Recall that it is a pre-flow, not a flow, because it is not satisfying the flow conservation property. Now for this pre-flow you can come up with a residual network. The definition of that residual network is same as that of a flow. You can verify that it is the residual network, and once you get a residual network, you look at an intermediate vertex with a non-zero excess flow. For example, you are looking at here. What is the excess flow? It is 16. So now you can try to push that flow to the neighboring vertices. Now you can see that there are two outgoing edges from V1. Which are they? They are V1S and V1 V3. And not that if you send it back, it is not going to be good. And push-relabel algorithms will never send excess flow at intermediate vertices back to the source vertex until it finds a max flow. So you have to somehow prevent sending flow back to the source, because it will create an infinite loop where you will be sending from S to V1, then V1 to S, and it will be repeated forever. That needs to be prevented, and push-relabel algorithms introduce what are called heights of vertices. We will see how that will help. And the height of a vertex is nothing but a natural number. For every vertex there is a height which is a natural number. And the height of the source vertex is defined as the number of vertices in the network. So here there are 6, so the height of S must be 6. Later we can see what height will do, and also the height of the sink vertex will be defined as 0. Assume that this network is modeling water flow from a water tank to a house. So the level or the height of the water tank should be greater than the height of the sink. So basically that is what is height is representing. And to start with, all intermediate vertices can take a height value 0. So not that. For the source, the height is the number of vertices. So the sink, the height is 0, and for all intermediate vertices, the height is 0. And this is a constraint that you are going to impose. To push a flow from a vertex U to a vertex V, you know that U must be at a higher height, and here push-relabel algorithms demand that the height of U must be 1 more than the height of V. Now see that you will never send a flow from V1 to S, because the height of V1 is less than the height of source, and during the processing no intermediate vertices will be allowed to get a height more than the height of the source. So this is what we set. To send or push a flow from U to V, the height of U must be 1 more than the height of V. Now see that there are 2 neighboring vertices for V1, S and V3. But look at their heights. The neighboring vertices are having heights 6 and 0. So both are greater than or equal to the height of V1. So by this constraint, push operation is not allowed. So now we will see what relabel is doing. So we need, if you want to push the excess flow which is 16 at V1, say to V3, you have to raise the height of V1 to 1. Okay, you can do that. You just increase the height of V1 to 1, and the operation is what is called a relabel operation. So relabel is relabeling the height of a vertex, actually which is relabeling to 1 more than the neighboring vertex to which you want to send the flow. So now not that, you can send a flow from V1 to V3, and 12 is the capacity, 12 is the capacity, and so you can send a flow with value 12. Okay, so 12 units you can now send along this. That is what you are doing. Not that previously the preflow was F1, now you are getting F2, and the excess flow at this vertex becomes 12. Here it was 16 reduced to 4 because you now pushed a flow value of 12 along this contour. Now look at that network F2, come up with a residual network and consider an intermediate vertex with an excess flow. V3 is having an excess flow of 12. Look at its neighboring vertices V2 and T, and what are their heights? Both are having heights 0, and the source is also, the vertex from which you want to discharge is again having height 0. So what you can do is, you can make the height of V3 1 by using a relabeling operation. Now suppose you are sending it to T. You can either send it to V2 or T. You don't know what will happen. The algorithm will send it to any one of these. Now assume that you are sending it along this. The capacity is 20. The entire excess flow can be pushed along that edge. Now you are getting F3, the preflow F3, and the excess values are getting adjusted. You can verify it. Previously it was 12. Now it is 0, and the excess flow at T becomes 12. Now you have the preflow F3. You get the residual network. This is the one which you can verify. Look at an intermediate vertex which is having an excess flow. What is the excess flow over here? It is 13. Look at its neighboring vertices. There are 3, and all the neighboring vertices are having heights greater than or equal to this vertex. So you have to now increase the height of V2 to 1. So just increase it. Now you can see that only one push operation is enabled, which is along this, because the height of V2 is 1 more than the height of V4. So the excess flow, which is 13, can be completely discharged through this conduit. So you will get a new flow F4 where you are discharging the excess flow at this vertex. Now this will get an excess flow of 13. So you are getting the preflow F4. You come up with its residual network induced by F4. This is the one. Look at an intermediate vertex having excess flow which is 13. Look at its neighboring vertices and see that now the height of this vertex is 0, and all the neighboring vertices are having height greater than or equal to 0. So use a relabel operation. Now you are using it to increase the height of this. Actually you can increase it to 1 more than the height of the vertex who is having the lowest height. Here 0, 1 and 1 are the heights of the neighboring vertices. You select the minimum height vertex which is T, make this height 1 more than that. That is what exactly the algorithm is doing. So the height of V4 is now getting to 1, and which enables a discharging or a pushing operation along this conduit. You do it, now you have 13 excess flow here. 4 you can send along this, you will get F5 as the flow, and not that the excess flows are getting adjusted. Previously here you had 13, now 4 is discharged through this, so it is becoming 9, and here it is increased to 16 from 12. Now look at this preflow F5, obtain the corresponding residual network. Look at an intermediate vertex having, or select an intermediate having vertex having excess flow of value 9. Look at its neighboring vertices V3 and V2. V2 is having height 1 and V3 is having height 1. So both are having height 1. So the minimum is 1. So make the height of V4 2, which is 1 more than the neighboring vertex height. So you are getting height of V4 as 2. Now you can send the flow back to V2 or V3. Both are enabled. Assume that the algorithm is selecting a flow across this. Both are enabled. Algorithm may select V2 as the next vertex also. It is possible, but you can analyze it in that way also. I am proceeding like this. So 9 excess flow was here. Now 7 is discharged or pushed along this conduit, and this flow is F6. Look at it. Come up with the residual network induced by F6. It is what you are having here. Look at an intermediate vertex there is an excess flow of 7. See the neighboring vertices, the heights are 1, 2 and 0. So, the minimum is 0. You use the relabel operation to make the height of V3, which is already 1, sorry, no need to relabel, you can already, you already have a push operation enabled along this conduit, do it. What is the excess amount? 7. The capacity is 8, so the full excess flow at here can be discharged along this edge. So, what you will get? You will get 19 here, and excess flow here becomes 0, and here it becomes 23. Now, this is F7. Look at an intermediate vertex in the corresponding residual network. Let us say you are looking at B4, excess flow is 2. Look at its neighboring vertices, only 1. And what is the height of it? It is 1. So, flow is already enabled. So, you can send it along this line back to B2. So, the complete excess flow here, which is 2, can be discharged along this. So, they are in the opposite direction. So, the net flow across this will become 11. So, that is the flow F8. Look at it and come up with the corresponding residual network induced by F8. Look at an intermediate vertex. Now, V1 is having an excess flow of 4. Look at its neighboring vertices. Only one neighboring vertex is there, which is having a height of 6. So, the algorithm will use relabel operation to make the height of V1 1 more than the height of the source. As I said, now the algorithm has found the maximum flow already, which is 23, and that is why it is sending it back. In the next lecture, we can prove that it found the maximum flow. Now, the algorithm will make it 1 more than the height of the neighboring vertex. So, it is becoming 7. A flow is enabled. So, you push that flow, which is 4 unit along this. So, 16 along that direction, 4 along the opposite direction. So, if you push that, it will become 12. Okay, this is the flow value F9. Look at it and find the induced residual network. And now there is only one intermediate vertex with a non-zero flow value, which is V2. And what is its flow value? Sorry, excess flow, it is 2. Look at the neighboring vertices for V2. Okay, and now there is also this that I am not considering. I am leaving that as a homework exercise. You can find it. Okay, I am not considering this. I am assuming that it is not there, and I am leaving that as an exercise. What the algorithm will do, you find how is it getting it back to source. So I am leaving it. And so these are the two neighboring vertices I am considering. One is having the height 7, other one is having the height 6. So minimum is height 6. So I will make the height of this 1 more than the height of S. So I am using relabeling to make the height of B2 7. So it becomes 7. Now I am not considering this conduit, take it, and so a flow is enabled across this because the height of this is not 1 less than the height of V2. So this is the only conduit which enables me to push. If I push it, 2 units will go back to S. So this becomes 11 and I am getting a preflow F10. Look at it and find the induced residual network, and now you can see that all the intermediate vertices are having excess flow 0. So now what you did is you sent back all the excess flows back to the source vertex. So in the residual network, no push or relabel operation is enabled, and what you do is you finish here, and you can prove in the next lecture that what you obtained is actually a max flow, and now you are getting a flow. It is no more a pre-flow because it now all the intermediate vortices is are satisfying the flow conservation property that the excess flow at every vertex is 0. So that is the basic idea behind push-relabel based algorithm. Now let us try to see formally what is a push operation doing. This is pseudocode that I copied from the textbook. You want to push a flow from U to V, and it applies when there is an excess flow at U and the capacity of this edge, remaining capacity, is greater than 0, and the height of U is 1 more than the height of V. And what is the action? You have to push a flow. What is its value? It is represented by this notation. The value of that flow you are trying to push along this edge, it should be the minimum of the capacity or the excess flow, whichever is less. Okay, if the capacity is more than the excess flow, you discharge complete excess flow, or you can only send a maximum of capacity. You can easily see that. So you find the amount of flow that you can push, and now you check. Suppose this edge or conduit is there in the original network, that is, it is present in the original network, then that means that is an existing conduit, so you want to increase the flow along that. And if it is not the case, that means you are sending it back, so you are subtracting. This is what we have seen from the basic Ford-Fulkerson method. If you are sending it along the same direction, you are adding, otherwise you are subtracting. Anyway, you pushed it, and after that you want to adjust the excess flow at U and V. At U it is decreased by that amount, at V it is increased by that amount. So this is the push operation. Now let us proceed and look at the relabel operation. You want to relabel the height of U, and it applies when U is overflowing. There is an excess flow at U, and all the neighboring vortices are having height greater than or equal to U. Then you want to make the height of U 1 more than the height of the neighboring vertex who is having the minimum height. That is what I am saying. You find the minimum height of the neighboring vertices and you make the height of H 1 more than that. So that is the relabel operation, and now we can look at the initialization part. You want to initialize the heights of all the vertices to 0, and later you are making the height of the source same as the number of vertices. So you initialize to 0 for all the vertices, and you initialize the flows along all the edges to 0, and then you set the height of the source as the number of vertices, and after that what you do is, for all the neighboring vertices for the source you are sending maximum flow. That is what I see. Why not that? You made the height, the flow along all the edges 0, except for the edges leaving the source where you made it maximum, the capacity of that conduit. And about the heights, you note that for all the vertices other than the source you made the height as 0. For the source you made the height of the number of vertices. And now you can look at the push-relabel algorithm. What is it doing? It just calls the initialize pre-flow operation. That is what we saw here. And after that, what is it doing is, while there exists an applicable push or relabel operation, then you select an applicable operation and do it. And you can see that only one of them, relabel or push, can be enabled at any time. So that is the push-relabel algorithm. So today we discussed about push-relabel based algorithms, where the algorithm proceeds by only looking at the neighboring vertices, and the flow conservation property is relaxed, then it do push or relabel whatever is enabled until no push or relabel operation is enabled in the residual network. If none of them is enabled, then you are assuming that what you found is a max flow. And in the next lecture, we shall prove that the algorithm is correct. Thank you.